Okay, so welcome everybody. Let's get it going now as people keep joining, but maybe we're ready to start. And this is an event in the AI Talks Chair Chalmers AI Talk series, which aims to bring some of the most distinguished researchers in AI today around the world to Chalmers. The original intention was to bring them to Chalmers in person, but this is in COVID times. We are running them online for the moment. And I'm David Dubashi, professor in the computer science department, and I, together with my colleagues, Frederick Johansson, who is also in the computer science department, and Umberto Piccini from the mathematics department, and Frederick Call from the electrical engineering department, run this series. And today it's our great pleasure to have with us one of the world leaders in an area of machine learning that may be called prediction online learning with expert advice. Nicolò Cesa-Bianchi, who is professor of computer science at the University of Milano in Italy. He has actually one of the best known textbooks or the textbook in the area, which on his webpage he advertises as Perdition, Burning and Flames, but actually it's Prediction, Learning and Games from Cambridge University Press. And this is a beautiful textbook account of topics in this area, from stochastic to adversarial learning. And he also has another very nice exposition. So these two we recommend to all our students. The second one with Sebastian Bubeck. It's a monograph called Regret Analysis of Stochastic and Non-Stochastic Multi-Armed Bandits, the Foundation and Trends of Machine Learning series. So both these books are highly recommended to all our students. So many of us have actually learned the subject from them. He's a former president of the Association for Computational Learning. He served as the action editor for Machine Learning Journal, for the IEEE Transactions and Information Theory, and the Journal of Machine Learning Research. And he's currently associate editor of the Journal of Information and Inference. He's also part of the world leading or the European Center. It's called the European Network of AI Excellence, ELIS. He's a senior member of the program committees in NeurIPS, ALT, and COLT. And he has received the Google Research Award and the Xerox Foundation Award. So very accomplished research career, and also from many talks that we have heard of him, is a great expositor. So it's a great pleasure to welcome him and hand over to Nicolò. I think Nicolò will go for about 40 minutes, and then we are encouraging people to write questions in the chat. If they need to be immediately answered, then Nicolò will answer them during the talk, but otherwise we have question and answer session after the talk when Nicolò is finished. Over to you, Nicolò.
Thanks a lot, Devdat, for the very nice introduction. I would like to say it's a pleasure to be here, but I'm afraid that here is not well defined for everybody. So it's a pleasure to give a talk, and I regret not being able to be there with you guys. That would have been, made perfect. But we'll try to do, everybody's trying to do our best. And this is a talk about online learning, but in a key that is more towards cooperation. Meaning that we would like to see whether, the extent to which learning agents can help each other to learn faster, okay? And everything will be, kind of abstract. I'm not really delving into applications, but I hope that the main messages will be clear from the talk, although the setting is a bit abstract. So this is an ongoing work that has several contributors, and we'll have hopefully more in the future. Some of them are Tom Cesari, Claudio Gentile, Shah Mansour, and Claire Monteleoni. Okay, let's move on. All right, so the main themes in this talk are that I'm interested in looking at learning agents that are operating asynchronously on a communication network, so they can talk to each other. And as I said, I'm interested in investigating the advantage of cooperating while solving a common learning problem, as opposed to being selfish and not share information with the other agents on the network. So one of the emerging themes that I find very fascinating is the fact that we'll be looking at online learning algorithms. And these algorithms they work on data streams. So they learn from a data stream that is being fed to them, and they solve a prediction problem defined on this data stream. And if you put a bunch of them together, and if you make them cooperate, you have sort of a co-evolution of this online learning algorithm. And I view this as a fascinating phenomenon that deserves investigation. You know, we had some nice discoveries in the course of these studies, and I will share some of these with you guys today. So let me give you a few motivating examples. Again, I'm not gonna you know, elaborate on these examples during the talk, but these are really motivating examples for the theory. So we know that by now, if you are a big player in finance, like in movies, or like Netflix, or in your Google or Amazon, you have your systems are geographically distributed, and you will have several servers that will adapt and learn profiles of the users. So this means that basically there is actually a network of agents that have to talk to each other in order to, you know, exchange information and improve their performance. Another possible application would be a mobile sensor network. For instance, you have these networks that they would like to monitor the environment. So they would like to predict some pollution, the evolution of the pollution in a certain zone. And again, they will, so they want to solve some common learning problem, and they want to solve it faster and better by exchanging information with each other. And this makes sense because, you know, the environment is distributed itself. So you need a network in order to get an idea of what's going on a certain scale. And in all these examples, we will be focusing on many things, of course. We'll be making assumptions throughout our study. But one assumption we'd like to focus on is that because, for instance, in finance, you need to make prediction at a very high rate, because data will arrive, you know, new data arrive all the time. And so you need to all the time making predictions. And because of that, you won't be able to broadcast and exchange information on a large geographical scale in between two predictions. Okay. Or maybe in the mobile sensor network example, you will have you're a mobile agent with some battery, and you don't want to waste your battery by doing long-range communications. So we will assume that the nodes are only exchanging information with their neighbors on the network. And we will also assume that the network is fixed, but not necessarily known by the agents. Okay, so far so good. So let's get a little bit more formal here. So the name of the game, if you like it, could be a problem of distributed asynchronous online convex optimization. So I'm giving you now the gist of the idea, and and then I will be, you know, making things more formal along the way. So you have some N agents that are sitting on the nodes of an unknown communication network, which is a graph, undirected. And the environment is modeled through an arbitrary unknown sequence of convex loss functions. So this sounds a little bit weird because it's the customary setting of online learning, but you haven't seen it before. It could, you know, could look a little bit strange. So the idea is that these loss functions may model like a linear regression problem with a square loss. So you have a sequence of data points, and you have a linear model, which is X, and you can measure the instantaneous loss of your linear model on the next incoming data point, if you like. And I'm abstracting and putting everything together in the notion of a variable time loss function. So it's a convex optimization problem, but the points on which I'm defining my objective are given to me one by one. It's always a convex problem because it's going to be a sequence of convex functions. But the sequence is also completely arbitrary. It is completely deterministic. There are no assumptions how the sequence is being generated, right? So this is the setting of online convex optimization. And the idea here is that I'm spreading out these agents that are learning sequentially on a network. So how does this work on a network? Okay, the idea is that it's still sequential. So every time step, a bunch of these agents will become active. So becoming acting means that they are requested to make a prediction. Okay, so we test them. Okay, let me know, make a prediction now about the pollution for the next half an hour or something like that, or the price of this stock. So the active agents will predict using their current models. Now you see that the X has also a V, which is the variable indicating the agents that is managing that model. It's one node of the network. It's V, is a node of the network. And each one of these active agents will pay some loss. For instance, if we are doing regression, we'll pay this square loss or whatever performance measure you like. Okay, so after they pay this loss, although since we are in an online learning scenario, we get some feedback information. Perhaps in the linear regression example, we're gonna see the label, the correct label of the data. Why? Because time is evolving, and we see, actually we want to predict the price of a stock, and we see how the price of the stock evolves. So we get feedback information after a short while, and we can update our model. And we can also share this information with the neighbors. The neighbors were not active. They were not asked to make a prediction. They were just sitting there. But we can tell them, look, we made a prediction and we extracted some information from the environment. We received some feedback from the environment. No, feedback is not distributed here. So we want feedback. You may say feedback is restricted to only agents who make a prediction will receive a feedback. So you may assume that agents who make a prediction will have access to feedback information because they were active at that point. So they were requested to make a prediction, and that fact makes them receive the information. Okay, so the feedback information is only restricted to those. So, but of course they can share information with their neighbors. Okay. So of course, I mean, I'm saying these assumptions may make sense in a certain in certain applications. In some others, they do not make sense. In some others, they have to be adapted. This is a kind of a very abstract scenario. I am assuming that accessing the feedback is costly. You have to make a prediction. You have to pay loss, and then you can access your feedback. And then you can decide whether you want to share your feedback, but you can only share it with your neighbors because you have a restriction in communications. So that's how the game works. So now you can share feedback with their neighbors, and the neighbors can also update their models, but they don't have to pay a loss because I gave them the feedback I received by making a prediction and paying a loss. So feedback is restricted only to neighbors in the graph, right? Okay, so how are we gonna measure performance in this model? So In online learning, the usual performance measure is called regret. And this is the following. So you remember there is a single sequence of loss functions. So there is a single sequence of data points that, if you like, and agents that have to make a prediction will receive this data point, or more abstractly will have access to the loss function. Okay, and if you like, because it's an assumption we will make in shortly, you can think of just one agent being active at each time step. This is sort of make things more concrete and simple to reason about. But our results will hold in a more general setting. Okay, so for any given sequence of losses that defines the environment, there's going to be a best global model, for instance, a best linear predictor. Okay, so this is just minimizing in the model space, is minimizing the sum of convex losses. So this is the best model that every agent would like to use, because it's going to be the best model for the problem that all these agents are trying to solve. So now we can measure the instantaneous regret of an agent using a certain current model with respect to the best global model. It's just the difference between the losses on the same loss function. This can be also negative, because this is the best global model, and this guy is using a specific one, which could be for that specific time step could yield a loss which is smaller. But in general, this is the best global model, everybody. Okay. So now we can define a notion of system regret. And this is like, okay, I might have a set of active agents. This may be just one or maybe more. So I average the instantaneous regret over the active agents, the instantaneous regret of all the active agents, and then I sum it up over time. Constraints to the global model, it has to belong to a model space which is shared among all the agents, right? Yes, but other than that, it's just a minimizer of the sum of the losses. Okay, I'm answering. Sorry, I should read it aloud, but I guess you can all see the chat. Not on YouTube. All right, I will read it aloud. So this is the question, whether there was additional constraints on the global model. Cool. So let's see. So first of all, now we would like to put the pieces together. So we pick an online learning algorithm and we replicate it in the nodes of the network. So which learning algorithm we pick? All right, there is a very usual suspect here, which is called online mirror descent. And this is the workhorse of online learning. Everybody is using this algorithm, and it has is a family with very simple members, like online gradient descent, which is just, if you like, the stochastic gradient descent, where the data are not stochastically generated, but just arbitrarily, deterministically generated. And exponentiated gradient, which is another member of this family. You might have heard of exponentiated gradient. So the common trait of this algorithm is that they need the gradient of the loss to work, because they are essentially gradient descent, although they may use different geometries for doing gradient descent as opposed to Euclidean geometry. But this is not important, really important here. So they all receive gradient. So for instance, they may get the label YT in linear regression, and then they are able to compute the gradient of the loss. And if we run them in isolation, we get a very nice behavior. We get as a single agent, their regret with respect to the best single model grows sublinearly with time, like a square root of t, and this is an optimal growth rate. If I divide up by capital T here, it means that the average loss of the sequence of models generated by the algorithm converges to the best global model at rate 1 over square root of t. And this is an optimal rate. All right, cool. There's dependencies, other dependencies here that are hidden, but dependencies on time is just square root of t. All right, so now I can say, okay, this looks like a good candidate. It's a very general, it's flexible. Let's put it to work on the network and let's see. Okay, for now, we just assume that one agent is active at the time. This agent gets makes a prediction, pays, receives feedback, shares feedback with neighbors. Right, let's see. Okay, let's work out a baseline. And this is pretty easy, no? So you just have to remember, if I sum up over all time steps, because I'm alone, I'm a single agent, then this is going to be my regret bound. Cool. So now let's see. Let's assume now that every agent will be active on some subset of the time steps, which is a partition of all the time steps. And over all of those time steps where the agent is active will suffer some instantaneous regret. Okay. Now, whenever he's active, he has to make a prediction and pays the regret. And the feedback, we can call the feedback a costly feedback because the guy had to pay a loss, made the prediction and pay a loss to get this feedback. But then he can share the feedback with the agents in the neighborhood, and these agents will receive the feedback without paying anything. They didn't have to make a prediction, but nevertheless, they will receive a feedback which they cannot really, which they can use to update their model. All right, let's see. This is a pretty easy exercise. So we know that the system regret is going to be the sum over all the agents of the overall regret of the agent. But every agent is running online mirror descent. So we know that the regret is square root of t, v, which is just the number of time steps where it's not a subset, it's the cardinality of the subset, of course, right? So the cardinality of the subset of the time steps where the agent was active. Nice. So we can just multiply and divide by the number of agents and use Jensen's inequality to observe that we get a dependence on the regret, a scaling, which is the square root of the number of agents. Okay. So if nobody is talking to each other, it just means that basically I'm doing my job on my subset of time steps where I'm active and everybody else is doing the same. So that's the idea. And, you know, if these things are evenly spread, so if we make every agent active for the same amount of time steps, this is essentially tight. So there is no way I can improve on this unless I introduce some form of cooperation. And now I want to see how much can cooperation buy me with respect to this baseline that regret, which is a system, the system regret depending on the number of agents. All right, let's see. Now I'm putting myself in a very nice and general setting. I'm assuming now, because I want to see, I want to decide what do agents know of the network. I have to decide that before I can do some more sophisticated reasoning. So let's see. I'm calling this oblivious network interface. It means that basically I take an algorithm, which is going to be OMD, online mirror descent, and I replicate an instance of the same algorithm on each node of the network. The initialization and the learning rate are the same for all the nodes. And moreover, each instance will make updates ignoring whether the feedback information comes, for instance, the gradient of the loss comes from a free feedback or a costly feedback. So either a node, whenever receives a feedback information, either because it was the neighbor of an active agent or it was active itself, it will make an update with the same learning rate, same everything. So this is a very generous setting in which I just take a OMD, plug it in, and let it run. No specific initialization. Each instance is oblivious to the network topology, to the location in the network, and I'm isolating the impact of communication while I'm abstracting from any network-specific tuning, because that's complicated. I don't want to get into that business. And right, so one thing that we will you may ask is how the convergence of gradient algorithm is ensured. This is the theory. Okay, so someone is asking how do I ensure that the algorithm is converging? And this is an online learning theory. I know that if I run online gradient descent or online mirror descent more in general on a sequence of convex losses on a bounded model space, or even on unbounded model space under additional condition on the curvature of the loss, then I know I'm going to converge with rate square root of 1 over square root of t. So that's guaranteed. So I now would like to see how much I can speed up this convergence because of communication. All right, cool. So let's see. First of all, I'm making an assumption here. It's going to be an initial assumption. Then we can try to relax it. And the assumption is, right, agents is going to be activated stochastically. Why not? Let's make this assumption. Maybe, you know, maybe it makes things nice. Maybe it's just not useful. So by stochastically, I mean that there's going to be one single active agent for the moment. And this active agent is drawn according to some fixed and known distribution over the agents. So now, you know, someone, the environment is deciding at random, is picking IID active agents from that. All right, so all the results I'm gonna show you in the next slide will also hold for this multinomial model, if you like, in which each agent has a probability P, each agent V has a probability P of being independently active at every time step. And I independently flip a coin to decide the subset of active agents for any given time step. So these two scenarios are pretty much equivalent in terms of our results. So we just focus on the first one, on the, right, not on the multinomial, but on this one here. All right. And the distribution is fixed but unknown to agents. So agents are oblivious to the distribution, which is completely arbitrary. You may say, all right, the distribution is focused on a single guy. All right, so that single guy is always active, and I am fall back to the theory of single agent online mirror descent. No problem. All right, so one key notion that will play a role in the bound is the notion of independence number in a graph, and that's the size of the largest independent set, and an independent set is the largest subset of vertices that are pairwise non-adjacent on the graph. Here is a nice picture of an independent set. Okay, I guess all of you know this, but just a reminder. And as you notice, that independence number is always smaller, not larger, let's say, at most the number of nodes in the graph. If I don't have any edge in the graph, then the independence number equals the number of nodes. But if I am on a click, then the independence number is 1, is constant. So dense graphs have a small independence number, sparse graphs have big independence number. And of course, sparsity and density have to do with the effect of communication. Okay, this is all intuitively clear. Let's see how it plays out in our theory. It plays out like the following. So now, if I run OMD with stochastic activation and oblivious network interface, which means that I'm not initializing, I'm not doing any trick to initialize OMD. So I'm just running off-the-shelf OMD on the network obliviously. Then I get, because of the stochastic activation, which does a magic together with the online learning analysis, I get a regret bound, which depends instead on the number of the agent. It depends on the independence number of the network, which is cool because that's smaller, right? Okay. All right. So this is the first message. Things help if I have stochastic activations, and even if with a single agent, I can I can get this improvement. And you can think of the following. So think, for instance, that we are on a click. Okay, if we are on a click, then everybody is talking to everybody else. So this means that if I'm sharing the information with everybody else, and everybody else is a copy of myself, it means that the state of the nodes, of the algorithms running on the nodes will be the same, because everybody has the same angle of view, has the same viewpoint on the stream of data. So, which means the following, that essentially alpha in the click case is going to be 1. So in the click, I'm falling back to the single agent bound because all the agents are actually one single algorithm running in a sort of a funny distributed way. Okay. As I pluck out, as I delete edges from the click, the communication goes down, and now my number of states goes up. So in order the network has to keep a number of effective states to keep track of things and make the regret small, which grows essentially like the independence number of the network. So the independence number of the network gives you the number of effective states that I have to use in order to get a regret of square root of t. And if I don't have any edge, then every algorithm is learning in isolation, and the number of states equals the number of nodes in the network. Okay, I find this cool. And this is something that is interesting, and the independence number pops out from an inequality which is totally graph theoretic and has to do with the fact that so the Q is the probability that an agent is active. The big Q is the probability that an agent will make an update. And making an update, you make an update whenever yourself are active, or a neighbor of you is active. Okay, so that's capital Q is bigger than little q. And if you sum this over any graph with respect to any probability assignment of the nodes, you always get this fancy inequality, which I kind of like. Lower bound, all right, so for all graphs and for some distribution Q, any online algorithm must have this lower bound. So even though the algorithm is initialized in a very fancy way and uses different, different learning rates, whatever, but you can see this lower bound pretty easily now, because if you go back here, right? So I make active only the red nodes, and then since the red nodes can only share information with neighbors, but the neighbors will never become active, communication is just deleted, and I'm running a system with an independent set of independent nodes whose size is equal to independence number of the network. They cannot communicate with each other, and I'm just using the bound for isolated node, which is tight in case the number of times each node is active is the same. Okay, I got a question here. Is the left-hand side of this to be interpreted as some fractional relaxation of the independence number? Yes, yes, yes. Again, this is a result in graph theory, and there are many proofs of this result, and there's definitely a relaxation. You can find a proof of this result in the proof of Turan's theorem, for instance, if I'm not mistaken. I believe so, yes. Turan's theorem contains a proof of this result. Cool. So let's move on now. I have 5 more minutes, so I won't be talking about bandits. I guess no, I have a bit more. I have 10 minutes, okay, but I want to go slow. So let's see what happens now if agents are activated adversarially, right? So let's say I got some very nice results when agents were activated stochastically. So about adversarial activation. So this means basically that the adversary is controlling both the loss sequence, the sequence of convex losses, so the data stream in a sense, and the sequence of nodes that become active. So now the adversary can play a game by making these 2 pieces of information collude with each other. Can it be playing a game? Can it play a game? We don't know. Let's see. So we can prove actually a pretty strong lower bound. Essentially, if the nodes are chosen adversarially, and if the algorithm is running with an oblivious network interface, which means really that basically the algorithm is always making an update whenever it gets some feedback information from maybe a neighbor, then the regret is going to be linear, which means that there is no convergence to the best model. There's no learning at all. So basically, adversarial activation and inability of distinguishing between updates, which means a simple algorithm, essentially an algorithm that makes an update, every time it gets some feedback without caring from, from whether the feedback comes from a neighbor or not. These algorithms are doomed, all of them. And the proof is actually kind of intuitive. So I can construct a star graph, and basically I can give a certain type of loss functions to all the nodes in the periphery, and a different type of loss function to the node in the center. So whenever the node in the center, so the different type of loss function means that it's a perturbed loss function, some loss function which does not correspond to the actual best model that all the other nodes believe. So this node will receive losses that correspond to a certain best model, but this guy will receive losses that correspond to a different best model. However, this guy, whenever it receives has to make a prediction, spreads the information around and misleads everybody else. He's an influencer and misleads everybody else. And these guys are just oblivious to the source of feedback because they're working within this oblivious network interface. So they will make an update that they don't care whether the update comes from the center or that comes because they were active themselves. And therefore, they will be systematically misled by the center. And if you choose the parameters right, you get a lower bound. Wow, okay, but now you can say, fine, but you are being really strict here. You don't want the node to know about the topology of the network. You don't want to know about the source of the feedback information. Let's try to relax some of this information and see whether we can tame these adversarial updates otherwise. Okay, so first of all, if you ignore, so let's assume you can distinguish between the source of feedbacks. So you ignore all the feedback that come from neighbors, so you don't have any communication, then you can have the baseline feedback we showed at the beginning, which is not exciting, but it's better than than linear. At least it's sublinear in time. Okay, maybe we can do something better, right? So we can do a click decomposition of the graph. So let's assume that the nodes now, they know their position on the network, and they know the network, so they can agree on a click decomposition. And basically, each node is only talking to the members in the element of the click decomposition, of the same element of the click decomposition. These guys in the click will be a single state. And now we will have a bound which scales with the click covering number of the network. But in order to do that, the nodes have to know the topology of the network, have to know their position, and have to compute or be given a click decomposition. Well, that's a lot of information, right? But it pays off because now I can get something better than n, because click covering number is always smaller than n. Right. So how about agents can also share their current models? Okay, it means the following, that I am suppose I'm talking about, I can use a bit more time. Yes, I can use maybe a few more minutes. Let's assume now that I compute a dominating set of the network. A dominating set is a subset of nodes such that every other node is adjacent to a node in the dominating subset. Okay, so basically the nodes whenever a node is active, if it's in the dominating subset, it can make a prediction. If it is not in the dominating subset, it can delegate the dominating node, the node in the dominating subset he is being dominated by, to make a prediction on its behalf, right? So now the number of states again will be just the size of the dominating set, which is the dominating number, because every node is delegating the elements of the dominating set to make a prediction. Okay, and so this is again, I'm beating because I'm not using this oblivious network interface. I'm beating the linear lower bound. I'm sidestepping the linear lower bound, and I'm getting a regret that depends on something which is actually even better than alpha. So the dominating number is always smaller than the independence number, which was our leading scaling factor in the stochastic regime. And click covering number, yeah, it's worse than the generally not at least as big as the independence number. Okay, so let's see. So this is a message that's saying if you allow more knowledge, then you can actually deal with more information. However, if the activation is stochastic, then even this more knowledge about topology and stuff won't help you unless you can do non-local communication. Because you remember the lower bound we had here, the one here just depended on the fact that if the adversary only activates nodes in independent subset, then these nodes cannot communicate with each other because communication is only local. Okay, so we have this bunch of results, and there's more about the bandit setting in which the nodes have a different amount of information. I'm not gonna dwell on these results because I think there's enough to be digested. But the idea here, for those who know the bandit model already, the idea here is that in the bandit model, essentially nodes won't be able to compute gradient of losses. So you cannot really run gradient descent. You have to run algorithms that rely only on the value of the loss as just a feedback. So the only feedback that these nodes have is the value of the loss. They cannot compute loss gradients. So now this entire business becomes a bit more complicated because if a node has some loss, I can share my own loss, but it won't help you, right? Because you have my loss, but you want to play, if you are not active, you may want to play a different action. But now I cannot simulate the loss of a different action that I would like to play because I only know the loss that my neighbor played, of the action that my neighbor played. So things become more complicated, so you need to have so the only way in which you can get an advantage through cooperation in the bandit model is because if all nodes are simultaneously active, then neighboring nodes, so nodes that are simultaneously active and they're neighbor of each other, they can use the loss information to decrease the variance of their loss estimates. So this boils down, but I'm going very fast, so only for people who know already about bandits, this goes down to a regret bound on this form, where n is the number of agents and d is the number of actions in the bandit problem, which is the leading parameter in the bandit problem, which boils down to the dimension of the problem. And if the dimension is more than the number of agents, then I end up again with a bound that is ruled by essentially by the independence number. But here I'm requiring that all agents are always active all the time. Otherwise, there is not real way of exploiting cooperation. Okay, thanks a lot. I am done, and I hope I didn't go over time. And thank you so much for your attention.
Thanks a lot, Nicolò, for a very nice survey of this new field of cooperative online learning. So the field is open for questions. Those who want to either now you can even ask it without writing it in the chat. You can say that you want to ask the question directly, and we'll unmute you to ask your question. So in the meanwhile, maybe Nicolò can ask you. I mean, I was confused about one thing. So, I mean, when you did the adversarial, the last adversarial result, you had the dominating number in the bound, but and and you made a comment that beats the lower bound in the stochastic, but that's a bit confusing. So, but the model was different because in the stochastic case, you were not allowing them to share the models, right?
That's right.
That's a different.
That's right. That's right. So yeah. So I am. That's completely true. Did I say it beats? Okay, I said it. Okay, it unfairly beats.
Yeah. So the obvious follow-up question is: if you allow the model to be shared in the stochastic case, what happens? Right.
Yeah, it's okay. I don't think. I think you will still end up with the dominating number, which is also already better. I don't think you can get any further advantage there. I don't have lower bounds. Honestly, yes, we didn't explore a lot this direction, and there are many ways of defining what you want to communicate, the extent to which you want to communicate it, and the possible delays in communication. So these are all, we explored some of these directions, but of course, there's many of these directions that can be explored. In the banding setting, I'm reading a question. In the banding setting, would it be interesting to consider a joint action for nodes in the neighborhood? Okay, so maybe nodes agree to make a joint action. So actually, I'm not sure. So I didn't explain it clearly, but essentially, suppose that you're doing a bandit problem. So in a bandit problem, you can only play an action at every time step. So your loss estimate has a lot of variance. You can only see the value of the loss function on one coordinate, which is the action you played. But now suppose that simultaneously all of your neighbors play their actions. So chances are that the actions played by your neighbors will be different from yours. So now suddenly you have a much better loss estimate because you get the information about the entries that you couldn't see because you played an action, but you could see because your neighbors played a different action. So that this diversity helps. Indeed, when the number of nodes in the networks is big enough compared to the independence number, then you basically you basically are back to the full info rates, as if you had the full information rate, right? You are back to the alpha coefficient. A more vague question: is it possible to extend this to a setting where the agents form in the communication graph when the agents form the communication graph while learning? For example, let's say that the agents are solving similar tasks, but not necessarily the same task. Then one agent would like to find out, yeah, this is like Emil, you're basically already there. This is something absolutely, totally, I mean, we are working on this. So yes, this is absolutely, I mean, this is the real question. So now, okay, this seminar, Emil is asking the real question and the seminar is answering the fake question. The fake question is the graph is there, and the agents don't know the graph though, which is the point in my court. However, the learning problem is the same for all agents. Now, the real thing is when it's a reality, my problem will be slightly different from yours, but to the extent our two problems are similar, we would like to capitalize on that. We would like to discover this and start a click or start sharing info, because we realize that if we share info, we are better off because our tasks are similar. Yes, that's tough though. So good luck. I mean, this is a question, of course, that can be asked. This is a question of multitask learning. So you can ask it in the batch statistical setting. You can ask the online adversarial setting. You can ask it in whatever setting, whichever setting you like. It's not really a matter of, you have to do online learning to solve this question. You can do whichever learning you like. It's just a good question.
Emil has a selfish reason for asking this question because he's working on a problem where that kind of setting arises. So maybe we can take it for discussion later.
Yeah, I know how to solve this question in a very because there's a sweet spot. So I had an old paper from 2009 that shows how to do this, although it doesn't completely answer the answer of Emil, because we know the graph there. But suppose that you know the graph, but the tasks are different. And you can still solve the problem in a nice way if you run, let's say, a perceptron. And so, which is a kind of a dumb algorithm, but it means that you are working with the online gradient descent, if you like. So you are using Euclidean geometry. Euclidean geometry will help you a lot, and you can end up with a bound that depends on the Laplacian on the graph. So, and this can be done, is reasonably easy to be done. Yeah, but we are working on more general examples now. Yes, this is a very beautiful question, and is a very active topic, multitask learning, and you can take it from very many angles. So it's just nice.
Okay, so while we're waiting for more questions, maybe another one that I can take the opportunity to ask. So in the Bandit setting, you gave the result, but so was it some kind of UCB type algorithm that gives you that upper bound?
No, XP3, because it's totally adversarial. Everything is
adversarial. But it was in a stochastic setting.
No, it was stochastic is just the activation of the agents, but in the Bandit setting, so again, everything is adversarial except for some results, agents are stochastically activated, but the loss is always adversarial. And in the case of Bandits, all agents are active at the same time. You may have things will work also if any subset of agents is active at the same time in the Bandit setting, and the neighbors in those subsets will exchange information. But then it becomes very ugly to write out the bound. The algorithm will work, but the bound will look ugly. If you just assume that all the agents are active, then you get a very nice scaling with the independence number of the network.
And why would the stochastic case is not interesting for some reason? I mean, the stochastic.
No, you can do it. It's still interesting. Yes, it is still interesting. You just have you see, if it's a subset of agents is stochastically active. Now, I think the bound will depend on the expected independence number of the typical subset of active agents, which starts getting a little bit murky, you see. Because if everybody is active all the time, then I know who my neighbors are all the time, and I can have a communication graph which is always, because I can always, in the Bandit case, communication is only useful if I exchange information with people who are active at the same time as myself. Are you guys still there?
Yeah.
Okay.
That's time to digest. So you have some results there with the various parameters of the graph in question, which is how you address this worst case example with the star graph. So I guess the star graph, the dominating set is 1, and so you get.
Yeah.
But I mean, if that was one way, but the moment you put that graph up, I was thinking that that's a worst case example. Maybe if you have other, if you say the graph has a degree at most d or something like that, you can get, or some other regular structure, you can get a better bound as well, and the lower bound wouldn't apply.
Yeah, we spent some time on this question, and then we gave up because it's unexpectedly hard.
You used you said this guy is the influencer, and the influencer screws up everybody. But you would, I mean, the intuitive thing that you would think is that if there are no such really bad influences, then you should not get this bad.
You're right. You're right. We thought that for a long time, but we couldn't prove any meaningful upper bound. No, yeah, it's open. This lower bound is not general. Sorry, this lower bound is general in the sense that it's not graph dependent. So for any given graph, you may have a sublinear lower bound. You're totally true. You got exactly the point. And again, I tried to solve this question and I gave up after some point because it was, yeah, it was kind of hard.
Okay, so now, Nicolò, you have to step outside your comfort zone and go outside of graph theory with the next question there. If you see on the chat, it's a more general question.
Yes, okay. The motivation, the motivation of these things is always the fact that we don't want to solve. We are not solving tasks in isolation. Thanks God, we are always being helped. And you know, you can view it from. There's a flip side to that, which is I want to learn from your mistakes, and I don't want to learn. I want to learn from my mistakes, but you know, to the maximum possible extent, I want to learn to the other people's mistakes. And or you can say I want to, you know, share what I learned with the others in order for everybody to learn faster. And I start from an abstract viewpoint. Ultimately, I'm hoping that you know, after I'm solving Emil setting in full, I'll come up with some practical algorithm. Online learning is used a lot in practice, and you know, these systems that work over stream exist in reality. They're used, so we can definitely hope to get there. This is like an initial step, and I'm taking a specific angle again, which is online learning, but there are several results using different learning paradigms or protocols. Yeah.
I mean, just to go to the practical application, I mean, the bandits are these days extremely hot because a lot of I mean, they're used in a very practical way by a lot of these internet companies to do all kinds of things. They're showing advertisements, etc., etc. Now, would the cooperative setting that you're talking about, would that be relevant to them in any way directly?
I have no idea. They wouldn't tell me. I don't work for them, so I know.
You got a Google Research Award.
Yes, but they don't tell me everything, right?
Okay, so I guess we.
There's another question by Giuseppe, and.
Okay, yes, sure.
Yes,
yeah.
There's Giuseppe. There's a paper with Hisham Mansour and Claudio Gentile that talks about the delay cooperation in bandits, and in that paper we address the issue of delays in communication. So we are assuming that you can actually get info from faraway nodes, but that info will come with the delay linear in the shortest path distance on the graph. And there's a beautiful trade-off between the scaling of regret in terms of independence number and the delay you want to tolerate. Okay, so you may want to tolerate up to the diameter of the network delay because that's the largest possible delay that makes sense on the network. And although we showed that there's a sort of an optimal delay that it fits most networks and gives you a provable advantage over over operating in isolation. And it's a delay that is proportional just to the number of actions in the bandit problem as opposed to the number of nodes in the network or any other parameter. So I invite you to check out that beautiful paper, which is called a delay cooperation in bandit something, in multi-armed bandits. Yes. And yeah.
All right, so we have run over our time. So unless there are anybody else jumps in now for the very last questions, we have to thank Nicolò once again for a fantastic talk and lots of stimulating discussion. And we hope that sometime in the future, I don't know when that will be, that we can really have him here in person. I mean, there are lots of virtual claps there already, and there are lots of people here who are interested in these kinds of topics. Lots of PhD students who are interested in online learning and Bandits and various versions of those. So hopefully we will have some interaction in the future. So thanks a lot again, and thanks to everybody else.
Thank you very much for the invitation. It was very nice, and yes, and I mean, I'm happy. The questions were wonderful, so I'm happy that people were interested. Thanks again.
Thanks
Bye,
again.
guys.
Bye, Nicolò.
Bye. Bye.